In this presentation, I will talk about the weld assessment using unstructured continuum element meshes. And my example is a simple intersection of a tube and a box section. The first thing I will do is I will import the finite element model, which was a Nastran bulk data file. So I have to scroll through the file browser and intersection type. Okay. This is the structure. This could be, for example, a corner section of a bogie. We can manipulate the view, just show the feature edges. And now, when we import the PDF file, we also import LSets, which can be found in the PDF. So we have sets that depend on the element type. So we have hexahedron elements with 20 nodes. We have tetras with 10 nodes. And we do have sets depending on the properties. So maybe this is a different material. And set 1, set 2, set 3 are sets that are not visible here in this GUI. So we might as well just delete these sets. Okay, now if we'll take a close look at the mesh itself, we can see that all the connections are performed with tie constraints or glue constraints, so it's not meshed through. And we do have different element types at the intersections. This is a hexahedron, and here we have the tetrahedron mesh. And I want to demonstrate how Limit is able to perform a fatigue analysis of welds on this structure. First of all, I'm going to give you a brief impression on the loading, on the load case I want to investigate. Here you see the structure. Actually, it's clamped here on this end, and I applied a vertical load at the end of the tube. So what we get is a bending moment here in the tube, which actually changes to a torsional loading, a torsional moment within the box section, and this gives us fairly high stresses here at local notches and stress concentration points. And we also see fairly high shear stresses here directly at the connection between the flange of the box section and the pipe. Okay, so how can we do the fatigue analysis for welds? In this case, we will use the sensor technology in Limit version 2013, which means that we will place sensors within the solid sheets, and for each sensor the program can calculate the membrane forces and bending moments, the local section forces actually, and based on the section forces we can calculate stresses in the welds and at the weld toes. We can do that in an averaged sense, which means that we can use these stress values we get for codes that are based on nominal stresses, and we can also use the structural hotspot concept like it is described by the IIW. And in our case, I will use the DVS 1612, which is a code for welding in the rail business. So, how can we generate sensors to derive stresses we can use for the fatigue assessment? The idea is that what you see here are actually parts. So every metal sheet is one part. The pipe is one part. The webs are one part, and we want to weld these parts together with different types of welds. And so that's also the workflow in limit. We have to define parts that should be welded together. Yeah. So what I can do, for example, if I want to weld this rib to this flange, I need two parts, or in limit notation, we need two element sets which can be welded together. I don't have these element sets here in this database yet, but what I can do, for example, I can replace and just show the hexas, and then I have, for example, a set where both flanges are included depending on the properties. So I can, for example, hide these elements, and what remains is this element set. And I can mark this element set and then push the right button and say create set. And I will just call it, for example, rib 1. Apply. And now I have, if I show all and push the rib 1, I have this one set. Yeah. So I can weld this set. I can touch this set and define it or select it for the welding purpose. Now I need a second set, for example, the flange, but I'm not going to go through all these set picking methods. Actually, it's really simple, and I have prepared sets I defined at an earlier time. So I'm going to open up the set manager, and I'm just going to import sets from a file I've created earlier. And now I have all sorts of sets. This means I can close this, and here I can scroll through all different parts. We can also change the colors depending on sets. And then it looks this way. Okay, so we have each sheet metal, planar or non-planar, is within a set. And one important thing is that you can only use these sensors for really thin walled structures, and each element set or each part must have one representative thickness, which actually is the smallest distance between two parallel faces. And each element may only be in one part set. Yeah, it's not possible that, for example, one element is part of the rib and at the same time is part of a web. So they have to be really mutual exclusive. Okay, so if we move to the sensors, and we want to generate these sensor elements we need for the weld assessment, then first of all, I have to define which element sets can be used for the sensor generation. And these element sets, they are called solid weld sets. So what I can do is I can activate all element sets in the sensor manager, and then I select all the sets that really are part sets, and I just select them. Wait. to stiffener, so everything is highlighted, and I just push the button change to solid weld sets, and then I get solid weld sets. Now I can see that the names have changed, and we have these solid weld sets. Here I can define the size of the sensors, the width and the length. The length usually is 2 times the thickness of the local sheet thickness, and the width is default. The default value is 1, but I will use 0.5 because then we have a better visualization of the sensors. Okay, so now next step is to deselect all the elements, and now I want to make a weld. I want to connect this rib with this flange, and always the continuous sheet is always picked as the first set, and all parts that should be welded to the first part are picked in as the second or third and fourth. So with this selection here, I tell the program that this set here is the first set, and the second part is welded to it. So I select the second part, and then I have here different topologies where I can generate my sensors. So if I click on the T junction symbol, then the sensors are generated, but we can see them because they're embedded in the mid-surfaces of these elements. So what I do is I exclude the element edges, and I go to transparency by clicking the spacebar, and we can see the sensor elements embedded in the structure. So for each sensor, our limit will calculate section forces, and we can, as I pointed out in the beginning, we can derive structural hotspot stresses or even averaged stresses to use them in combination with different codes or guidelines. Okay, maybe a second weld between the tube and the web, or both webs. So what I do here is I select the tube, which is the master or the first element set. Then I pick one element of web 1, one element of web 2, and then I first change the snap tolerance. In this case, I will increase it to 1 millimeters, and then I push the Auto Create Sensors button again for T-type topology. And if I make the model go to the transparency mode, then you can see the sensors embedded in this structure here, and maybe even a third position. Here I will change the snap tolerance to 0.1. Actually, the snap tolerance is important in cases where we have tied the structure, because then the snap tolerance defines the contour, or actually the positioning of the sensors. That's a parameter which can be modified and depends on the local structure. So in this case, I want to weld this. It's an overlap where this overlaps actually the pipe. So the first element I select is the pipe, and then I select an element on the bottom surface of this flange, because that's the touching surface. Then I push the overlap symbol, and limit generates the generates the sensors in here. So let's take a look at that. What you see here are sensors placed along the weld toe on the tube, and we even have sensors here on the flange itself. So we can also assess section forces coming from the flange. Okay, so for the demonstration purpose, I think we have enough sensors here in the structure. I can close the sensor manager. Now, if you are familiar with the shell assessment or the assessment of shell structures in limit, then the further steps are easy and clear for you, because these sensors have the same topology as shells. The only thing is that these sensors are generated in a post-processing step, and what limit actually does, it imports the deflections of the solid model for each load step, and based on these deflections we can calculate the strains in the sensor. And sensors actually are shells, so we get a bending moment and membrane forces, and this way we also get like a linearized stress distribution over the thickness of the solid, and then we use either the average values for nominal stress approach or the structural hotspot values for the second approach. Okay, so we have the sensors. The next step is actually to define the loads. In this case, I have 4 steps in my OP2, but actually I just want to import the last step. So I will call it FZ because it's a loading in a vertical Z direction, and it was the step 4. Okay, so this way I will import the last load case of my OP2. I need some loads, and I will produce them directly from the FE result. But actually, I don't want to have 100% of the load FZ, but only plus minus 20% as a fatigue load. So I change this value to 0.2, and then I copy this load, call it FZM from minus, and I put a minus sign in front of the factor and apply. And now I have actually a fatigue loading situation where we have plus minus 20% of the FZ load acting on the structure. So actually the stress range is 40% of FZ. Yeah? We don't really need a spectra, because if you use the DVS 1612, it's a fatigue strength assessment, and we just need actually the threshold value, but the cycle, the number of load cycles is not relevant for DVS 1612. Now with this missed, I can close the load manager, and the next step is to use a setup manager. And I can, for example, if I want to define this weld here, I change my selection filter to geometry elements. These sensors are not common finite elements, but inside of limit they are called geometry elements. They are different objects. So if I click this and I activate or click one of these elements, I can use my right mouse button and say create setup, and I can select it, and then what you see is similar to the way we do the shell definition. You see the thickness and actually the positions of our assessment points P5 and P6. Now in this case we want to perform a DVS 1612 analysis. and we have to define a few data down here. We have to choose the material, which is okay. We want to have a double-sided fillet weld with half the thickness of the shell as a dimension of the throat. So I just say T times 0.5, and I copy this value to all my positions, and then I get this picture here. So what will limit do? Limit will use the stresses calculated on the top and bottom surface, and will perform a fatigue analysis for the weld toes in the points P5, P6. And furthermore, based on the section forces and membrane forces, we will calculate the stresses in the fillet, and we will compare the stresses to the notch cases defined here, where the first notch case refers to the loading direction parallel to the weld. The second notch case refers to the loading condition transverse to the weld direction, and H is the shear. F2 actually is the worst notch case in that code, which is used for the both toes. Now the code actually is a nominal stress code, so I just switch the stress type to averaged, which means that we will get an averaged stress in the middle of the sensor, and since the sensor has the dimensions of twice the local thicknesses, we actually get a averaged stress at a distance from T, from the local thickness, away from the intersection of the parts. Okay, so with apply I can close this, and we have the first of our welds is defined. So I can do the same thing for this here. Still the filter is correct, so I choose this, I create setup, choose the web. Now I want to zoom in and see where we are located. So we get this picture here, and again this time I want to use a one-sided full penetration weld, for example. So blue is the first set, and the dimension of my weld is T, and D is actually the distance between the mid-surface and the toe. So this is minus T times 0.5. Okay, now here is the symbol, and this means that actually we have welded from the inside, which is not possible, so I have to switch, and now I have a welding situation from the outside. Yeah? And again, we can sweep the position and sweep it to the other side, so this also is welded from the outside, and we are okay this way. Now we have to I forgot actually to define the code, which should be done here, and I have to redefine my dimensions. We have the situation welded from the top times 0.5. Actually, the top of a part is defined according to the surface that was picked when we generated the sensors. So by picking the webs, both webs from the outside, I defined the top direction, the local top direction. Okay, minus T. And we are fine. This is okay. Maybe in a check we will change the position to the other side just to make sure, and it looks fine. It's welded from the outside. I've defined the geometry, and I will change the stress type to average since we're dealing with a nominal stress code, and apply. Okay, the last weld is actually the overlap situation, and I can create the setup for this here. This is maybe a bit more challenging concerning the type of weld. Actually, this is welded from the top, and the toe is here on the bottom. So actually, for the blue set, we would define T minus 0.5 times T. Yeah. So this way we will check the toe as on the right side of the shell, and we will have we will check the root on the right side of the weld, and we have a toe up here. And for this case, we can just use the DBS1612. I again forgot to select the code before I define the values. It's welded from the bottom, T and T times 0.5. Minus 0.5, which moves then the root all the way in, which is representative for the flange, and the web and the pipe itself has only toes running around the weld, and we see the notch cases here. And I want to use average stresses, and also here average stresses. And actually, the setup is done, or one possible setup is done for also this situation here. Apply closes this setup. Okay, now I have 3 setups defined, and my next step is to define the job. I just want to use 2 CPUs. I'm going to say create job 1 DBS1612. Apply. The interface preference is Nastran, so I choose Nastran X64. E denotes that we will have an English output to the result files. In a second step, I have to choose a result file, which is an OP2, intersection type OP2. And now I have to select the setups I want to use and the loads I want to use. And we're all set. And then I can run the job. In order to visualize the results, the job must be marked, and then we can push the View Result button. After that, the limit viewer will open up, and we can take a look at the results. The sensors cannot be seen here because they are embedded in the solid structure. So we can change the display and toggle away the shell or the element edges, and then we end up with this view here showing feature edges and the sensor elements. Sensor elements within the viewer are treated as normal shell elements. And if I select the result type, for example, maximum degree of utilization, we get this picture here. And what we see, we can see the areas that show higher loading or higher degrees of utilization, which was actually this corner point here. We also have higher stresses and higher degrees of utilization here at the end of the flange. We had high shear stresses in the web, and this is shown with a high degree of utilizations in this area. We can actually switch through the assessment points. For example, for the cross section of the welds, we have the toes. We have 2 root points, root 2, point 2 and 3. So that gives us high values in here. Maybe even more interesting is to check out the utility depending on the loading direction. So longitudinal or parallel to the weld, we have low degrees of utilization, high shear values we have here in the area of the web and here in the upper flange, and the highest values of utilization are not the highest, but also high values are calculated for the transverse direction, which is shown here. For the sensors, we have the same possibilities as for shells. We can also use the query function. So what you do is you have to select the 2D elements because they are embedded in 3D elements. So if we pick elements or sensors, then we have to make sure that we hit the shell. So we select 2D, push the query button, and then we can check out the results for the single elements. And you can see here the degree of utilization as well as critical load cases, the critical point, and the notch cases used for this analysis. Okay, so that's just an overview of the basic functions doing fatigue assessments for welds based on unstructured continuum element mesh models. And there will be further videos and tutorials for specific parts of using the sensors. And I am finished with this presentation. Thanks for the attention.